Hello students, in this video I will discuss force due to a multiple charge system, and first of all for random distribution of charges when the charges are discretely randomly located at different points. Now for calculating the force in this condition we have the superposition principle. First of all, suppose we have different charges q1, q2, q3, qn. Suppose we have a n charge system with position vectors r1, r2, r3, rn, and let us suppose that we have a force experiencing charge q located at a position vector r vector. Then the force on q due to q1 will be F1, due to q2 will be F2, q3 F3, and qn will be Fn. So these are the different forces acting on q due to the different charges. Now in such a case, the total force exerted by the system, the whole system, is given by the superposition principle, and it states that the net force experienced by a charge due to a randomly distributed system of charges is equal to the sum of individual forces. The vector sum of individual forces. This is superposition principle. Now here, as per Coulomb's law, F1 vector will be 1 upon 4 pi epsilon naught q1 upon r vector minus r1 vector modulus cube into r vector minus r1 vector. We already obtained this formula in under the topic the Coulomb's law in terms of position vectors. So F here, F1, the force due to the first charge, and here the order is force experiencing charge, its position vector, minus force exerting charge. Force experiencing charge minus force exerting charge. The position vectors will be in this order. Similarly, F2 is equal to 1 upon 4 pi epsilon naught q2 upon r vector minus r2 vector magnitude cube into r vector minus r2 vector. Now if you find for the nth charge, it will be 1 upon 4 pi epsilon naught qn upon r vector minus rn vector magnitude cube into r vector minus rn vector. So these are the individual forces, and hence by superposition principle the total force will be given by the net force will be F is equal to 1 upon 4 pi epsilon naught. You can take common, you have to add all these terms. So 1 upon 4 pi epsilon naught we can take common, as well as q we can take out common, and it will be q1 upon r vector minus r1 vector magnitude cube into r vector minus r1 vector plus q2 upon r vector minus r2 vector magnitude cube into r vector minus r2 vector plus qn upon r vector minus rn vector magnitude cube into r vector minus rn vector. In short, we can write this as q upon 4 pi epsilon naught summation I equals to 1 to n qi upon r vector minus ri vector magnitude cube into r vector minus ri vector. This is the total force. This is the formula for total force experienced by this charge q due to this randomly distributed system of charges. Okay. Now next will be second, uniform distribution of charges. Now we will find out the force exerted by a uniform distribution of charges. Generally in this topic we will find out due to a charged body. A charged body will have a large amount of charge. A small body, even small body, will have a large amount of charge, so we can assume that the charge is uniformly distributed over the body. Suppose we have and first of all we will find the charge is distributed over a line, uniformly distributed over a line. Suppose we have a linear charge, uniform distribution of charge over a line whose length is L, and suppose we have a charge Q at position vector R vector. Now we want to find out the force due to this linear charge distribution. So we will consider an infinitesimally small part dl of this length with position vector r dash vector, and the force due to this dl vector will be df vector. Now first of all we will find out this df vector and then we will integrate this value to get the total force. Now let us suppose that the charge on this part is, this charge is dq. Therefore, so df is equal to 1 upon 4 pi epsilon naught q dq upon r vector minus r dash vector whole cube into r vector minus r dash vector. Force experiencing charge minus force exerting charge. Now we have the value of dq will be, suppose if lambda is the linear charge density, then dq equals to lambda dl. Charge per unit length and the length is dl, so when they will be multiplied you will get the charge on this part, dl part. So therefore df is equal to 1 upon 4 pi epsilon naught q lambda dl upon r vector minus r dash vector whole cube into r vector minus r dash vector, and therefore f is equal to integral of df over the line, and it will be q upon 4 pi epsilon naught, being constant you can take outside, and it will be line integral of dl upon r vector minus r dash vector whole cube into r vector minus r dash vector. This is formula to calculate the force on q due to the linear distribution of charges. Okay. Now let us suppose that if the charge is distributed over an area, then here we can replace this line by a surface whose area is S. Then again we will consider an infinitesimally small part of this area in such a way that its area is ds and the charge is dq with position vector r dash vector. So now we will find out the force. So df equals to 1 upon 4 pi epsilon naught q dq upon the same formula. Suppose sigma is the areal charge density, then dq is equal to sigma ds, and therefore this value will be, for dq you will write sigma ds, and for calculating the total force you will take the surface integral. This will be surface integral, and okay, we missed here in the previous derivation we missed lambda here, So in this particular derivation, it will be sigma ds upon r vector minus r dash vector whole cube into r vector minus r dash vector. This q upon 4 pi epsilon naught being constant can be taken outside the integral. Now in case if the charge is distributed over a volume, then you can replace this by a volume suppose we have a volume distribution of charges like this, then we will again consider an infinitesimally small part of this volume with position vector r dash vector, and we will consider an infinitesimally small volume here with position vector r dash vector, and we will find out the force, and then we will take the integral. So df is again the same formula. Now here, if rho is the volume charge density, then dq will be equal to rho dv. Here the charge is dq and the volume is dv, and the volume of the given volume is, the given object is suppose v. Then df equals to 1 upon 4 pi epsilon naught. Here this value will be rho dv, and the net force will be the volume integral. Here the volume integral, and it will be rho dv. This will be the formula. Now if suppose we have if we have such a condition that there is a charge located at some point, and near that charge there is a random distribution of charges, there is a uniform distribution of charges over a line, over a surface, over the volume also, means all the four conditions are present, then the total force will be given by the combination of all the four formulas, and in that case F will be equal to Q upon 4 pi epsilon naught summation I equals to 1 to n Qi upon r vector minus ri vector whole cube into r vector minus ri vector plus Q upon 4 pi epsilon naught lambda dl upon r vector minus r dash vector whole cube into r vector minus r dash vector plus Q upon 4 pi epsilon naught surface integral sigma ds upon r vector minus r dash vector whole cube into r vector minus r dash vector plus over the volume Q upon 4 pi epsilon naught over the whole volume rho dv r vector minus r dash vector whole cube into r vector minus r dash vector. So by using this formula, you can calculate the net force experienced by the charge.